I hope we won't have interlapping talks because I'm also somewhat talking about LQs, but maybe it will be from different aspects. So yeah, let me share my screen and let me know if you see it. You see it?
Yeah, we see it.
Okay. Still.
Yeah, you're.
Um, yeah. So yeah, I'll be talking today. Or first of all, nice to meet you, everyone. I'm Tom, working at Stalker. We're developing together with a wide range of partners Starknet, and one of them is to mention. I think we've been working together almost 2 years now. I'm not sure. Um, and working together on building Starknet, on building all the tooling and the developer frameworks around it. So pleasure to meet you. I'll be talking about basically what's the idea or what's the main problems we see today in blockchains, what prevents them from fulfilling their potential or their promise, and how we want to help solve it in Starknet. Yeah, so a few words about myself. I'm Tom, I live in Israel, specifically in Nahalal. If you're familiar with it, this was supposed to be my, I don't know, job title, but I'm basically doing whatever Starknet needs. And you can follow me on Twitter. And before we dive into how we solve the problem, let's first understand what the problem is. Right, so first let's start with the blockchain. Blockchain started with Bitcoin in 2008 when Satoshi basically introduced Bitcoin with some implementation and some Bitcoin white paper to the world and started working since then. And then Ethereum in 2015 made another huge leap, basically generalized what Bitcoin did, which was a blockchain for a specific application for payments, uh, to a much basically general computation, taking the same idea of what Bitcoin did and expanding it to general computation architecture. Um, so blockchains are here for a while, but we don't see any really widespread adoption of it. And I think that the main or the first blocker to this is its slowness, right? So where does this come from? Why is this the case? And maybe one word before I go in. I assume you have some technical background, and I assume you have some blockchain background, but don't hesitate to just stop me and ask any questions. I don't have a lot of things to say here, and I think I have 30 minutes or 20 minutes. I don't know. But anyway, feel free, okay? Okay, I hope. Okay, so in general, today, when we want to talk about value, for example, about money, um, so when we want to expand it beyond, I don't know, agreeing on something with our friends, we want to expand it to a nation or maybe to a worldwide economy. Basically, what we do is we use some trusted parties, for example, banks or other institutions, and we basically delegate the accountability of the whole integrity of the system to those trusted entities, which are backed either by, I don't know, some well-known reputation or or a state. And if I want to transfer, I don't know, funds to Max, the way I do that today is through those institutions. I basically go to them and I ask them to transfer um, my funds to Max or to someone else. And usually it works. It works. It's very fast. It's very convenient. But some may argue that this has downsides. I won't talk about why this is the case. I hope you also think that if you joined today. But blockchain basically, uh, Bitcoin initially created a new way to solve this issue of how do I interact on value without having a centralized party to do that. And basically, the way Bitcoin and any other blockchain that exists today um, offer to solve that is that you don't trust anyone, but you verify everything yourself, right? When I send a transaction to Max, the way that nobody else trusts nobody is just I propagate the transactions to everyone, as you can see it, and everyone execute those transactions, and then everyone knows that I transferred I don't know, those dollars to someone, right? Does this make sense? I mean, there are many other things about blockchains, but in a very high level, this is the main idea, and the construction with the proof of work or with block hash and stuff like that gave a way to implement this idea. Now, when you do that, you basically sacrifice two things, as we said. One is privacy, right? Because at least in the naive implementation of that, everyone sees all the transactions. So everyone specifically also knows how much money I own and what interactions I do. So that's the first thing that it's sacrificed, and we won't talk about today. But the other thing that it sacrifices is scalability. And why is that? Because in order to allow anyone to participate in this network, the rate of transactions or the amount of computation that I require from each node is limited by the weakest link. So if I want to be able to participate without having a massive, I don't know, servers or farms, or I don't know, just using my laptop, then it creates a limit on the amount of transactions that can be done in the network. And this is the main reason why we have scalability problems today. So for example, Bitcoin is, I don't know, 10 transactions per second, 20 transactions per second. Ethereum is a bit more, but it's nowhere near something that can satisfy worldwide need, right? And I think this is one of the main reasons why it doesn't do that today. Okay, any questions on that? Please say no. Okay. Great. So now I want to introduce some notion, and then we see how this idea or mathematical concept can help us solve the problem that we saw earlier. And validity proofs is a mathematical protocol which uses cryptography. And I'm not sure I'm the right person to describe it in a way that would blow your mind, but to me, this blew my mind in the same way that, I don't know, the first time I heard about public key and private key cryptography, it blew my mind that you can do something like that. So this is, to me, was the same kind of eureka moment. So what is that? Validity proofs are basically a way for, let's say, two parties, Alice and Bob, to interact in a way that if Alice executed a program, I don't know, she computed, she went through a database and saw that my name is not included there, right? She executed a program. Then she can take this execution and prove it to me, Bob, that it is true without the need for me to re-execute it, right? So Alice can convince me, and I don't need to trust her. I just need to trust mathematics, that she searched through a specific database and my name is not there. And the only thing I need to do is to verify this proof. Sounds like magic. It is a bit magic, but it works. And basically, the nice thing about that is that we have computational integrity, meaning I don't trust anyone, and I know that the computation was done correctly, right? So how does that look like? And what's the nice thing about it? Let's say I have, in the context of what we said before, we have a lot of transactions, right? I don't know, 100K transactions that many people transfer the money between one another, right? So if before I had to re-execute all the transactions to know what's the amount of money that everyone has after that, now I can suddenly give those huge amount of transactions to an entity which is called the prover. The prover will execute the transactions and will generate a proof that the state after this execution, meaning how much money does everyone have, is true. And the only thing I need to do is to verify this proof to get convinced that this is the case, right? So is this clear in some way? Do I need to give another example? I think you're nodding your heads. Okay, sounds good. Now, the nice thing about this proof and why it allows us to scale is that the cost or the time it takes to verify this proof is exponentially smaller than the computation itself, right? And just to give a graphic estimation to what exponentially smaller means. So if, for example, this line is the amount of transactions that I want to execute, this line shows the amount of work that I need to do in order to verify them, right? So if it's very, very small, then the amount of work I need to do to verify them is approximately the same. But even though I increase the number of transactions in a linear way, the time it takes to verify the execution of those transactions starts to become almost constant. And this is the power of log, which again is a very nice concept. But what it allows us to do is that the sequencer or the prover can take the large amount of transactions, right? Do a large amount of work, but then propagate to the network only the proof itself. Okay, I will explain it in a minute. But okay, does that make sense? Or do you believe me? Okay. Sounds good. And a nice, even though it's not 100% accurate, a nice way of having like a mind model of what are validity proofs. So validity proofs to computation is something like what a zip is to a file size, right? It allows you to take a big file, compress it, while still having the integrity that this file is the same one that we had before. The compression here is, I don't know, linear, and here it's exponential, but this is a nice mind model. Any questions? There is a question? Yes. Live.
Hello, can you hear me?
Yes. Hi.
Oh, perfect. You mentioned all that stuff about Merkle tree, am I right? And Merkle proof inside the Bitcoin.
I didn't mention Merkle tree and Merkle proof. We can, but
I mean, that's what you explained, that you got some Merkle tree and we validate only Merkle proof instead of execute all of transactions, as I understand you, right?
No, so we have a different kind of proof. A Merkle tree and a Merkle proof allow me to basically to take a set of items, right, and create a commitment to them with the Merkle tree. And then a Merkle proof allows me to verify the existence of a specific item in a commitment in a log amount of hashes compared to the size of the set. But validity proofs basically take this idea and expand it to any computation that you want, not just the inclusion of an item in a set.
Okay, yeah.
Right? So basically you can take any computation that you want, and maybe, actually I'm not talking about it, but you can take any computation that you want. I don't know, write a program, you want to prove that the 100 elements of a Fibonacci series that starts with 2 elements is something, right? Write this program and you can generate a proof to its validity.
Mm-hmm. Okay.
This is called validity proof. Specifically, as you can see on my shirt, we are using a system which is called Stark, which is an acronym for something, but this is a way to implement validity proofs. But the nice thing about them is that you can execute any program.
Mm-hmm. So in the end, it's based on conception based on Merkle tree, but it's not. Okay, thank you.
It's not based on, it has many different mathematical algorithms. We can expand on that, but maybe let's see if we have time at the end.
Yeah, okay, deal.
Yeah, okay, good. Okay, so now we are at Act 3, and this is Starknet. And Starknet is basically how do you take this concept and implement it in a blockchain in a way that allows us to solve the previous dilemma that we have with regards to scalability, right? The dilemma that we have was, on one hand, we want anyone to be able to trustlessly verify what is the state. But on the other hand, this means that I cannot increase the amount of transactions because everyone have to re-execute them. So now let's solve it. Okay. So these are validity proofs. Starknet and ZK Sync are two examples for networks that implement it, right? But basically now we have two entities in the network. We have the big computers, right? Everyone sends transactions to them. They are the equivalent of miners, if you're familiar with this notion in Bitcoin, but let's call them the sequencers or the provers. And those entities basically get transactions, sequence them in some order, execute them, and generate a proof, right? And this proof, together with the block, is then sent to the networks of nodes of people who want to participate in the network and know what the state is. And now, instead of being of having to re-execute the full transactions that you have in each block, you only need to verify the small ZK Stark proof, the small validity proof. And you know that the block is valid and that the state that you have is really the state of applying this block. Does that make sense? Okay, and now we have this beauty that on one hand, we can have very big machines and execute a very high amount of throughput. And on the other hand, still allow anyone to run a client who participates in the network and verifies it. Nice. So in a very high level perspective, how does Starknet look like? So we have the sequencers, right, that validate and execute bundles of transactions and construct a block. Those are the sequencers. Then we have the provers, which takes those blocks and create a proof to their validity. And the nice thing about Starknet is that it's an L2 for Ethereum. And I won't steal the show for, I didn't get who is it from L2Bit, but for L2Bit, but on a very, very high level, this is all being verified on Ethereum. And so we inherited the security of Ethereum, which is, again, a very, anyway, it's very nice. And at the end, we have the full nodes, those clients that can just verify those proofs and knows what the state is. Okay. Now, a few things about Starknet, or I'm now going back to just describe what we did in the past 2 months and what we had in mind. But when we went to build Starknet, we basically had there was always few options to choose from. And having in mind that we want to build an infrastructure that will serve, I don't know, decades ahead, things were built from first principles. So first of all, we're using Starks. As I said, there are other options for validity proofs. Maybe it doesn't say a lot, but Starks has no trusted setup. What is a trusted setup? Very briefly. For other proving systems, for example, Snarks, you need to have some ceremony in which some keys are being generated by multiple people. And basically, they are used to initialize the system. And then you have to ensure that everyone destroyed those keys and they're not using them, right? So it means that there is always a trust point in the beginning of the network. So Starks doesn't have that. It also is probably the fastest prover that exists. And I didn't discuss it, but generating the proof is a very, very heavy computation. So you need to be able to do it very fast. And it is also quantum resistant, meaning the only assumption that we are using is the existence of a hash function, which is a quantum resistant assumption. So it doesn't break under the existence of quantum computing. So this is the first choice that we did, going with Starks, not with Starks. The second choice that we did was to go with a specific VM that is tailored for proving, instead of going with the existing VMs that we had, for example, the EVM, the Ethereum virtual machine, that was tailored for Ethereum, not for proving. The main reason for that was that it allows us a much better performance, a few orders of magnitude. And the trade-off was, do we appeal for already an existing ecosystem of tooling and developers, or we choose that? And that was the choice. I think it paid off. And also it allows us to have much more flexibility when we design the network. So we're not, we live on Ethereum, but we're not, we don't have to implement every change that is done to Ethereum. So this is a bit on some choices that we did along the way. Yeah, so I reached the end, a summary of what we did. So Starknet or generally Validity rollups basically gives you the same guarantees that blockchain gives you, but without the need to re-execute, right? And this allows the decoupling of who executes the transactions and who can participate and validate the network, right? At first stage, it's about scaling, right? We said we have two sacrifices in blockchains. One is that everyone can see every one transaction, and one is that we don't have scale. So we're first solving that. Next stage is privacy. And the nice thing about proofs, which we didn't discuss, is that they can also offer you privacy, but not today. And whenever we had the choice of what to do, we decided to build from first principles and to look into the future and to the performance of the network. So that's what I had to say, and thank you very much again. I hope it was clear and not too high level and not too detailed. I would love to hear some questions, or in general, talk about anything that you want. I'm not sure if I'm out of time or not.
Somebody has any questions? It's probably a good time to ask them.
Any questions?
Okay.
Hey, yo. It's me again. It's not about Merkle tree. It's about Starknet. I'm wondering, so in the end, it's L1 solution for EVM, yeah?
Starknet is an L2.
L2. Okay.
Yes, it's built on top of Ethereum.
Uh-huh.
So the source of truth is the state of Starknet contract on Ethereum. I didn't dive deeply into it. I just wanted to give the idea of how to use proofs to scale blockchains, but I can elaborate on that if needed.
Yeah,
what's the question?
it's quite interesting for me because state it's I would say complex stuff on Ethereum. It can't sync it because it's global. And how is, as far as I understand, you doing some batches of changes, pack it and execute on Ethereum, or how it works in the end?
Okay, so let me go back to here. So what's being actually done on Ethereum is just the verification of the proof, right? So we have an L1 smart contract, which, so smart contracts on Ethereum are just, you can think of them as programs with state, right? So this L1 smart contract basically implemented the verifier, the Stark verifier. So if you give it a proof, it can verify it and output if it's true or false.
Oh, okay.
Then we create a Stark proof for a block. We send it to Ethereum, to this smart contract, and then it accepts it only if it's valid. And then when we want to update the state of Starknet, we're basically going to the Starknet core contract, and we tell it, please update the state from S1 to S2, right? And this Starknet core contract asks the verifier did you see a valid proof to this state transition?
Mm-hmm.
And if the answer is yes, and there are other checks, but let's omit them for a second, then the state of Starknet progress forward.
Okay, I see. So you compute only verifying on Ethereum, but all stuff is on your blockchain, right?
And do exactly.
Okay. And you got some state?
Yes.
Is it global, same with Ethereum, or it's up to applications?
What's the question?
You got global state in Starknet?
The state that we have is, in a sense, very similar to the state of Ethereum, right? It's an address space where in each address you have a contract code with storage, right? The contracts are written in a language that can be proven. It's called Cairo. We didn't dive into it at all, but
Yeah,
Cairo
okay.
is basically a high-level language that we developed at Starkware. And the nice thing about it is that you can prove its execution, right? If you take, I don't know, a Rust program, you don't have the ability to just prove its execution. But Cairo, which is a very Rust-like language today, Max can tell.
It is.
Yeah, is you can compile it to an assembly that can be proven.
Oh, okay. It's clear, your flow. Okay.
So the contracts are written in Cairo, but you have general computation, you have composability, you have all the good stuff that you have on Ethereum, just to scale it.
Okay, thank you.
Thanks for asking.
One more question.
Yeah. I'm here. No rush on my side.
Hey, thanks. Hi, I'm Joseph. So my question is like, why don't you use Rust then? Like, why did you come up with your own language if it's so similar to Rust, as you said? And what other tech stack do you use?
Okay, great question. So in order to prove a statement, you need to be able to represent it in what's called an L, which is an algebraic intermediate representation, right? So it's a set of polynomials that you can then translate into a proof. And if you go back to the early days of Starkware, so when we wanted to create a proof to some statement, we handcrafted those polynomials for each computation that we wanted to have. For example, the first application that we did was a spot trading, right? So we created in polynomials, which, as you can imagine, is not a very trivial thing to do, the statements that are relevant for spot trading. I don't know. I verified the signature, I did the settlement, etc., etc. Okay. And then we understood that this is not scalable. I can't expect anyone to understand how to write things in polynomials, right? It's very equivalent to ASICs. If I want to compute something, I have to create a card for it. Okay. So then what we did was to say, okay, let's take a step backward. And what we'll do is we'll create a polynomials that describes the CPU, right? I can basically define some opcodes, and then I can define some way that they can operate on some registries. And then I can feed it a program and prove its execution. Maybe it was too complex, apologies. But my point is the following. Rust compiles to assembly, which can run on Metal, on CPU. But there's no way to prove it because it just doesn't go through anything that can be proven. So what we did is we created a specific assembly, which is called Cairo assembly. And this assembly is a specific, it can be proven because we built an L polynomials that describes the architecture of this CPU. Now you couldn't just describe a regular CPU because it is highly inefficient. It will be the ability to generate proofs to those programs will be infeasible, right? So we created a VM architecture which is tailored to have very efficient proof, right? And then you can say, okay, so maybe write a compiler from Rust to this assembly, right? So it turns out it's not that simple because there are some inherent difference in the way things works. So originally we started with some very low level language, and then we tried to improve it. And then we realized that we just need a much better high level language, and we created it with a lot of influence from Rust, but with the changes that are needed in order to allow it to compile to our specific assembly. I hope it makes sense. But the short answer is because we can't. Okay.
Okay, one more question.
Yes.
Yeah.
Oh, okay.
What about the second part of my question? What are the tech stack do you use?
Sorry,
Except for Cairo, what are other languages do you use? Is it the only one?
You're asking, do I have other languages which I can use to write smart contracts?
No. I'm asking if you use in Starknet other languages than Cairo.
Okay. Yeah, so Rust is used for everything but the smart contracts mainly. So the prover itself is written in C++. The sequencer was written in Python, but then it was very inefficient. So now it is being rewritten in Rust. I mean, there's endless amounts of tooling and stuff around Starknet. I assume this was not the question, but basically the stack is now being Rustified almost completely.
Nice, thanks.
I've got a question about the language.
What's your name? Apologies, I missed it, but I feel we're already...
My name is Yaroslav.
Yaroslav, hi, nice to meet you.
Nice to meet you. We've got the same flow. We've got own language in company. It's efficient to work with that blockchain as database. And we've got, I can say issue, but maybe it could be better. It's a people who work on company language. How you solve an issue with the people? You learn everyone from scratch. You hire strong developers and teach them, or how you work in Starknet?
You're asking how do we handle the challenge of teaching people Cairo?
Yes.
Yeah, this is one of the main challenges. I think one of the great benefits that we had is that right now is very influenced by Rust. So if you're coming from Rust, it is very natural to learn. I don't know if Marek is here.
It's here. He's waving.
So I think he can speak a lot about that. Marek was very influential in the design of design and even implementation of the new version of Cairo. And really, initially, the meme of the community was that learning Cairo is hard, and this is, the ethos. If you were able to learn Cairo, then you are worthy, or something like that. But I think it was, it attracted some kind of people, but it didn't allow many to come. And now, when we made it very similar to Rust, and also just much better in general, then it lowered the barrier and allowed many more people to come. But in general, we focus on that a lot. We have a team of developer advocates, which is almost 10 now. And we also have, I would say, 10 more people in the community, which is not from Starkwell, that are like ambassadors of this. And we have a lot of workshops, a lot of much longer programs that teach people Cairo and Starknet. But yeah, it is one of the biggest challenges that we had and still have.
I would add here that I'll explain my case if you don't mind. We've got some incubation program with the grants. For example, it's working really good. And when we came to some I don't know, country, with a good marketing, it's great for us a lot of people who learn our language. It's really good schema. Yeah, thank you.
Nice, thanks.
We have time for one more question if somebody has one.
I'm ready.
If anybody else wants to ask.
Nobody? Okay. It will be Tomek, like from our team. So
Where is it?
he's here. You don't see him because he sits there.
I know how you look like.
Yeah. I was just about to say that you've seen me enough times, but I do have a question. You said about privacy and the proofs, that proofs could provide privacy, and I'm curious about that.
Okay, sure. So do you see my screen?
Yeah.
Okay. So okay, I won't find another presentation. I will speak and you will believe me. So one of the other nice, so we said we have a nice property of those proofs that they are exponentially smaller to verify, right? But another thing that you can, and this is where the term ZK, which means zero knowledge, you can also generate those proofs in a way that leaks zero information about the computation itself apart from the statement. I'll give you an example. Let's say that I'm trying to prove to you that your name does not exist in the database. So I can construct the proof in such a way that, now there's feedback, that you will learn nothing about the database itself apart from the fact that you do not appear there, right? Or to give another example, I can generate not only the proof, there needs to be some changes to the blockchain, but I can generate the proof in such a way that you will only know that the state has moved from S1 to S2, but you will learn nothing about the transactions that were executed. Right? Does that make sense? If you're asking what's the technical way of doing that, then it's a bit more complicated, and we need to talk about how do we generate those proofs. But this is also a property that you can have, right? They don't only give you validity, but they can also give you a zero knowledge about the computation itself. And for example, Zcash, if you're familiar with it, is a blockchain that uses validity proofs in order to create a private payment network where you have transactions that are being propagated, but the transactions leak no information on who's the sender, who's the receiver, and what's the amount. And so you basically don't know what happens there apart from the fact that it is valid, which is, again, mind-blowing, at least for me. Does that answer the question?
Yes. Yes, it does.
We'll reach there as well, so stay tuned.
Okay, so thank you, Tom, for your presentation.